So let's get started. So we were discussing multiple linear regression last time. So it's a generalization of the simple linear regression, and which helps you accommodate, like, if you have more predictors. So in the advertising data set, you had the response as the cells, and the predictors were radio, newspaper, and TV. And we considered that you can run separate simple linear regressions on each of the variables, but that may not be the correct thing to do, because some of them may be correlated, and then the correct idea is to look at the predictors together. So the approach we discussed last time was you take this linear model, so y equal to beta naught plus beta 1 x1 up to beta p xp plus epsilon. So this part is your linear model, which has p variables, p predictors, to be more precise, and we interpret beta j as the effect, average effect of y when you increase xj by 1 unit and when you hold the other predictors fixed. So how do you estimate the coefficient? So you can do it using OLS, that we'll see soon. But suppose you have estimated the coefficient beta naught hat to beta naught p, and this is sufficient because we have discussed that in a linear model, estimating the coefficient is sufficient to identify the model. So suppose you have identified, suppose you have estimated these coefficients, and now you have this equation. So this is an analog of this straight line, or the least square line that we saw in the simple linear regression case when p equal to 1. So for p equal to 2, this would be a plane, and for larger p, this defines a p-dimensional plane, and it's very difficult to visualize. So how do we estimate the coefficients beta naught hat up to beta hat p? So we fit this, so we try to minimize the residual sum of squares. So we write yi hat as beta naught hat, beta naught, beta 1 hat xi1, and so on, and you take the square difference with yi, squared them, and then add them up. So that gives you the residual sum of squares, and the coefficients are those which minimize this expression. So you write it for any beta, and the one that minimizes this are your coefficients beta naught hat to beta p hat. The minimizers are called the multiple least square regression coefficients, and you can write them explicitly in terms of a matrix formula that we are not going to discuss here. But in the simple linear regression, we saw a closed form expression is using just the variables xi. That simple formula will not be available in this case, because we are in a little bit more complicated setup. But this inversion, matrix inversion, can be, if you're familiar with that, then this is like a p by p matrix, and you can invert it, and that can be done very quickly for not too large p, and then you have an estimate of the coefficients. So we'll soon see how to run least square multiple linear regression in R, but if you run the regression in R, then this produces the following output. So here you see that you have intercepts, so this can be thought of as beta naught hat, this is beta 1 hat, this is beta 2 hat, this is beta 3 hat. So here are your estimates, so corresponding to this beta naught, this is the beta naught. So okay, so these are the corresponding variables and these are the coefficients. These are the beta naught hat, beta 1 hat and so on. And you get the corresponding standard error and you also get a significance level. But the interpretation now is a little bit different. So in the simple linear regression case, you are interpreting it as like what happens if you change the TV or radio or newspaper by 1 unit, but here when the same interpretation holds when you hold the other predictors fixed. So you fix your radio and newspaper and say that, okay, if I put $1,000 additional only in TV, then the sales go up by 45 units. So yeah, in the same fashion, so if you spend an additional $1,000 on the radio, that leads to an increase in sales by 189 units. And why is that? So you have approximately 0.189 in the radio coefficient. So you multiply it by $1,000 and then you get that it's the sales increases by 189 units. So an interesting thing to observe, well, we have not shown, but like if you run the simple linear regression with newspaper, then it will show that the p-value is significant. So it's not shown here, but what it shows that if the sales in newspaper increase as the budget in newspaper increases, then the sales also go up. So newspaper has an effect on the overall sales, but if you run the multiple linear regression, that does not show up because the p-value is quite high, and we have discussed that a high p-value means that that variable is not significant. So in R, always like you will see very small values and these are the codes. So you set your significance level, and then triple star means very significant, and so on and so forth. So if there is like no star on the side, that means the p-value is higher than your cutoff, the usual cutoffs, and then you can interpret this as it does not significantly affect the cells. Any question on this slide? Okay, so what happened here? So we discussed that if you just do a simple linear regression, then you can see that newspaper coefficient is significantly non-zero, but if you do a multiple linear regression, then the coefficient is, it's not zero, but like it's not significant. So the p-value is higher. So you can interpret that is very close to zero. So what happened here is just changing from simple linear regression to multiple linear regression gives you a clearer picture. So what happened is that the newspaper and radio variables, they are correlated. So in the data, like the amount of budget spent on newspaper and radio, they are like either both of them go up and go down, in this case, in some way correlated. So you see that the coefficient for the radio is significant because this is less than any suitable cutoff, let's say 0.05. So radio drives sales high. That means that radio has significant effect on the sales, and because radio is correlated with the newspaper, that means that if you run the newspaper versus cells simple linear regression, then it will show that the newspaper has also a significant effect on the cells. So if you mute your radio data, so the newspaper becomes a surrogate for the radio. So and then the credit the radio's budget has on the cells, that is given to the newspaper. So when you run a multiple linear regression, the picture actually is very clear that newspaper is not significant, but the idea is because they're correlated, if you just omit this radio, then that onus is taken up by the newspaper, and it shows that this is significant. So multiple linear regression is very important of this because of this phenomenon of correlation. Here is a more absurd example. It's when you run a regression of shark attacks on ice cream cells, but there is a confounding variable, which is high temperature, which is associated with both the ice cream cells and also the shark attack occurring in the beach. And so if you run the multiple regression on this type of data, it will show that temperature will have high, will have a significant effect on the shark attack. Sorry, the other way around. So it's temperature will have a significant effect on the ice cream cells, but the shark attack will not. So in the presence of one confounder, so in this case, it's like the temperature is kind of called the confounder. So if you include that, then you see that two variables may be independent. But if you do not include the confounder, then the picture will look like that these two variables are kind of dependent. That's called a spurious correlation in statistics. So what are some important questions in the multiple linear regression setting? So first we ask, okay, you have the variables x1 to xp, so is at least one of them useful in predicting the response? Okay, so suppose I have certain that, okay, there is at least one of them which affects your response. Then the next question is, okay, so do all the variables, they affect this y significantly, or is there like a subset of them? And if it's like a subset of them, which subset of this x1 to xp, the predictors, affect y? And then the other two questions is like, how, if you try to fit a linear model, how does it fit the data? And if you try to predict it using this, the entire set of predictors or like a subset of them, how well do you predict the data? So the first question is there a relationship between response and predictors? So in the advertisement data set, we'd be asking like, okay, is there a like a relationship between the cells and this TV, newspaper, and radio? So in simple linear regression, we only have to check that whether beta 1 equal to 0. So it's, recall that beta 1, so in the simple linear regression, y equal to beta naught plus beta 1x plus epsilon. So if beta 1 is 0, then the predictors has no relation with the response. But in this case, we need to ask if all the regression coefficients are 0 or at least some of them are non-zero. So your two hypotheses are beta 1, beta 2 up to beta p equal to 0. So, if that is the case, then I cannot, okay. Yeah, so if beta 1, beta 2 up to beta p all are 0, then you just have y equal to some constant plus epsilon. So, none of the predictors actually affect your response. The alternative is at least one of them is non-zero, and then the question is finding out which of the which one is non-zero and which are like 0. So, this test is performed by computing the F statistics. So, you will see that this looks like this, the R square statistic that we discussed last time. So, you have to take the, you take the TSS, the total sum of square, you subtract the residual sum of square, and then you divide by the residual sum of square. But it here we divide by the RSS instead of the TSS. And also we include this numbers p and n minus p minus 1, and those are related to the degrees of freedom of the F distribution. Here also this TSS is yi minus y bar whole square. So, this TSS is explaining the amount of variability in the data, and this RSS is the amount of residual variability. So, you predict using yi hat and your errors are yi minus yi hat. So, you take the square and then sum it up. So, that is like the residual variability in your data. So, if you are under H naught, that is all these coefficients are beta 1 up to beta p are 0, then you can show that this F statistics is around 1, and if you are under H1 is that if one of them is non-zero, then you can show that this is larger than 1. Actually, we expect it to be larger than 1. So, on an average, it's larger than 1. So, if your F statistic or the value that you computed from the distribution is significantly larger, then you actually reject your null hypothesis, or you say that, well, we have evidence that one of them is non-zero. You can also do like compute the exact power of the test, etc., if you assume that your errors are normally distributed. So, if errors are Gaussian, then F follows an F distribution, but for if you are working with large n, this assumption can also be relaxed. And in the advertising data set, R actually computes the, I mean, you can actually observe from the output of the advertising data set that R actually computes the p-value of the F statistic. So, it is this one. So, this is your residual standard error. So, this is the F statistic, and you see that the p-value is very small, 2.2 times like 10 power minus 16 or something like that. So, p-value is very small. That means we have discussed that when p-value is small, then we reject the null hypothesis. So, we have significant evidence against the null hypothesis. So, in this case, this means that okay, at least some of the predictors, TV, radio, or newspaper, has some effect on the cells. So, H naught is like cells is independent of this TV, radio, newspaper, and H1 is at least some of them has some influence, and we can see that this F statistics is so. So, the p-value is essentially 0, like very close to 0. So, we have a strong evidence that at least one of the media is associated with the increased cells. So, there is also additional information in the R output. So you have individual p-values. So you have this individual p-values. They say that okay, if you fix the other responses, suppose you fix the newspaper and TV, and then if you want to evaluate the effect that radio has on the cells, then it says that this is significant. So the p-value is small. But 0.86, like in newspaper, the p-value was 0.86, so it's not associated with cells, and there is like a spurious correlation. So that's what we have discussed a little while ago. And we asked the question, so suppose one of the p-values is small, then does the overall F statistic has a small p-value also? So why is that the case? So it means that suppose you have one of the predictors which has small p-value, it would mean like, okay, it will have some effect on the response, and then you can just argue that, okay, so this predictor is significant, that means at least one of the coefficient is non-zero, so F should also have a small p-value. But this is flawed for like large p. So under H naught, there is a 5% chance of any of the p-value to be below 0.05. So that's how this. So under H naught, all the coefficients are 0. So you have under H naught the p-value is uniformly distributed, and then it has 5% chance of falling below 0.05. So if p equal to 100 approximately, like you will see 5 p-value that are small. So the individual t statistics will give you wrong information. So suppose even if all of them are 0, then in this case, at least 5 of them will, I mean, there is a high chance that 5 of them will be small, and then you will argue incorrectly that because of that, like at least 5 of them will have a significant effect on the response, but we assume that our H naught that in H naught that no predictor has any effect on the response. But AF statistics actually take all of this into account, and AF statistics does not have this problem. So we come to the next question. So we already discussed whether any variable has some effect on the response. Now, once we have decided that, so we have to decide which of the variables are important. So you are given the predictors x1 up to xp, so you are interested which subset of them. So suppose you want x1, x2, or x2, x3, like which subset is actually associated with the response. So in the advertising data set, this would be like, okay, so you have TV, radio, and newspaper. So which subset is important? So if you look at the data set, so you look at the output, so you'd be thinking, okay, so this TV and radio would be the important subset. It's the collection TV and radio, and newspaper would be out of this subset. So this picking out the predictors which are important, this problem is called variable selection or feature selection. And ideally, we'd like try out different models. So suppose P is 2, then we consider 4 models. The first model is there are no predictors. In the second model, there is only x1. In the third model, there is x2. and the fourth model is x1 and x2. We compared their RSS, and then we say that, okay, which model fits the best. There are several criteria with which you can evaluate your model fit, like which of these four model is a good fit. So some of them are Mallow-CP, AIC, BIC, and adjusted R-square. So AIC stands for Akaike's information criterion, and BIC for Bayesian information criterion. So these has something to do with like a penalized regression, and we'll see them in more details in chapter 6. But there is a fundamental problem with this approach. So you see that for 2 p equal to 2, we consider like all the models. So there is like 2 power 2, it's like 4 models. So if there are like p coefficients, then you have to fit like all possible subsets. So all possible subsets of a p dimensional like of p numbers is like 2 power p, and if p is like 30, then you end up with 2 power 30 models, which is close to 1 billion models. So this is not like a practical approach, like you fit all the models and see which of them, which one fits the best. So there are 3 classical approaches that alleviates this problem. They're called forward selection, backward selection, and mixed selection. So forward selection is the first one that we're going to discuss, and it's like we start with a null model, so you have no predictors. Now you fit p simple linear regression. So for the advertisement data set, so you first fit the sales versus the TV, then you fit sales versus newspaper, then you fit the sales versus radio. Like you fit like 3 separate simple linear regressions, then you choose the one with the lowest RSS. So you compute the residual sum square for all the simple linear regression, and you consider the model with the lowest RSS, and then what you do is like, so suppose the model with the TV that gives you the lowest RSS, so you include the variable TV in your model. So now your model has only TV. So you started with a null model, so now your model only has TV. So what does that mean? So it means like we are selecting a subset of the p variables. So the p variables were TV, newspaper, and radio. TV gives you the lowest RSS, so now your model has only TV. So you have selected the variable or the predictor TV from your 3 predictors. So once we're done with that, so what you do is then you consider models like just TV and radio, TV and newspaper. So you iterate this process, always adding the variable that results in the lowest RSS. So suppose TV and radio give you the lowest RSS, then you add the variable radio with your TV. So now you have selected TV and radio from the 3. So when you do that, so if you do a simple computation, so you are going like, first you are choosing among p, then you are choosing among p minus 1, and so on. So if you compute the total number of models that you are considering, so you end up getting 1 plus p by p plus 1 by 2, that's simple computation, and then you're only considering models which is like a quadratic in p. So instead of 1 billion, so it's like, if it's like a 30, so this is close to 900 models instead of like 1 billion models. So what we are essentially doing is like we have a large, so in this case it's like 3 predictors, so it's easy, but if you have like a large number of predictors, what you do is instead of considering all possible models, we go like a step-by-step approach of adding the predictors to our subset, and this method gives you like a practical way to do that, because like we are way below this, like the original thousand, like the original billion models we were considering. And you can also choose a stopping rule, so you are just adding predictors one by one, and you can say, okay, so if I add a p-value and see that, okay, this p-value is too large, we can always drop the variable and we do not add anything else. So the backward selection is the other way around. So in the forward selection, you start with a null model, and then okay, so we start with the null model, and you gradually add the predictors. But in the backward selection, you start with the full model. So you say that, okay, all my predictors are important, x1 up to xp. So you say that, okay, TV, radio, and newspaper, all of them are important. And then you remove the variable with the largest p-value. So the one with the large p-value means that it's not significant, so you remove that. So instead of adding one by one, so you are like deleting one by one. So you refit the model and then iterate. So it's like the same approach as the forward selection, but you do like in a backward fashion. Again, you can choose a stopping rule. You can stop when the largest p-value is very small. So when the largest p-value is small, that means that at a particular point we are considering the model, then like the remaining variables are, all of them are significant, so you stop when your largest p-value is small. And there is also this mixed selection, which is a combination of forward and backward selection. So it's like you start with a null model, do forward selection until the p-value is larger, and then you go back to this backward deletion procedure. So you delete some of the variables, and then you iterate this process, and then you see which model gives you the perfect fit. For that, you have to come up with a stopping rule. So in practice, we usually do forward and backward selection. So mixed selection is like a combination of them, and it's more like a trial and error approach. So we saw in the linear regression setup that a residual sum of square and the R square, they are used to quantify model fit. So in the multiple linear regression setup as well, these two quantities are used to quantify the model fit. So R square is the proportion of explained variables in the response variable. So R square is like the TSS minus RSS by TSS. So for advertising data set, if you consider the full model, then R square is 0.8972. But if you omit the newspaper, you see that the R square goes down a bit. But the drop is not significant. So when you add newspaper, so do the reverse procedure, then the R square is a little bit higher, but that not high. So what we're essentially trying to say is that newspaper does not affect the R square that much, but it's true in general. So when you add variables, then R square actually increase. But you can decide on which variables are important by just looking at how much the R square increase. So again, yeah. So having only a tiny increase in R square is evidence that newspaper provides no improvement on the model fit. And in contrast, that the model with only TV has R square 0.6119. So suppose you fit the simple linear regression model with TV, then R square is 0.6119. So this is, you compare that with the one where we have TV and radio. So you omit the newspaper. So when you omit the newspaper, you have TV and radio, and that's 0.89719. So this close to 0.9. So if you had R square for the TV as 0.6, so you just include the radio, and then the R square goes up by like 0.2. But when you add the newspaper, then the R square does not go up that much. So you can interpret it like this. So you only have TV, then you add the radio. So there is a large improvement in the model, and then you include the newspaper, then the improvement is not that much. RSS is defined, RSE, the residual sum of standard error, is like defined in the same way as in the linear regression case. So you, the simple linear regression case. So you take the RSS and then divide it by n minus p minus 1, and then you take the square root. So you can compute the RSE for the advertising data set. You can see that for the full model, the RSE is 1.686. If you just use TV and radio, then that is, you omit the newspaper, then the RSE is smaller, 1.681. And if you use just the TV, then the RSE is 3.26. So again, higher the R square, the better the fit. Lower the RSE, better the fit. So they are in some way opposite. So because R square is like the explained variability in the model, and then RSE is like the explained is the residual standard error. So it quantifies the error in the model. So the lower the error, the better. So if you have TV, just include the TV, then the RSE is very high. So it has a very high error. So if you include TV and radio, then the RSE is low, 1.681. And RSE also shows that if you include the newspaper, then the RSE again increases. So TV and radio seems like the optimum combination in this setup, and it has the lowest RSE. So adding radio to TV improves our model, but further adding newspaper makes it worse. But here the RSE is different from R square, because if you include a larger model, then the R square always goes up. But if you include, like if you consider a larger model, then RSE does not always go down. So even for if you consider a larger model, then RSE can go up. So there are other ways to check the model fit. So you can plot the models in R, and then you can try to notice whether there's pattern of fit. So this is sort of this is like the plot of the cells with TV and radio. So we have included the newspaper primarily because it's not that important that we have seen, and also like we cannot visualize higher dimensional data directly like this. So an interesting observation is like if you look at only the points which are close to this line radio, so you omit the TV, or if you only consider the points which are in the line radio, so you omit the close to the line TV, or that is you omit the radio, so then the coefficients tends to be negative. And if you consider both TV and radio, then the coefficient seems to be positive. So if you consider something like a point here where both of them are positive, TV and radio, then the error is also positive. So in this case, we can say that, okay, we can suspect that TV and radio have a joint effect on the cells. It's like not TV is affecting the cells or the radio is affecting the cells, but like if you are using some combination, then like maybe their interaction is actually affecting the cells. So those are models. Those models are called models with interactions that we'll consider later. So this is called the synergy or the interaction effect between two advertising media. And there may also be nonlinear patterns, so you can try to fit a curved surface through these data points. But since we are talking about linear models in this part of the course, then we'll not be talking about whether that curved surface is a good fit or whether that's like a bad fit. So once we fit the multiple regression model, so it is straightforward to predict y in terms of this x1 to xp. So you have your coefficients beta naught hat, beta 1 hat up to beta p hat. So you just plug in your new x1 to xp and say this is your prediction. So this is what we have discussed before. So the true population regression plane looks like this. So this is a generalization of the population regression line, and then this is the generalization of least square regression line. So this is the least square plane. So how far these two are apart, they determine what's called the reducible error that we have also seen before, and there will be another component called the irreducible error. So how good an approximation of the linear model, how good an approximation the linear model is for fx, that is given by this reducible error. So the linear model estimates the best linear approximation to the true surface. So the original surface may be nonlinear, but we are only considering the best linear approximation. So the inaccuracy in the total potential reducible error is called the model bias. We have seen that the reducible error can be broken down into bias and the variance. So if the actual linear model is correct, then and you choose and if you try to fit a linear model, then the bias is small. But as we have observed before, even if you estimate the data perfectly, so even if you estimate the function f perfectly with your plane, then there is also another error because of the variability of the data. So that comes from the excess noise epsilon. So remember that y equal to beta naught, beta 1, x1, so on, plus an additional epsilon. So because of this additional epsilon, there is what is called the irreducible error that we also saw before. And we need to consider this irreducible error when we do prediction intervals. So here we distinguish between confidence interval and prediction interval. So prediction interval is also like a confidence interval, but like for the predictions. So when we talk about confidence interval, it's like what are the chances that your fx lies between these two numbers, and the prediction interval is like what is the probability that the your predicted value lies between these two numbers. So when you talk about fx, we do not consider the additional error epsilon, but when you consider like the confidence interval for y or the prediction interval, we also account for the additional epsilon. So for example, in the advertising data set, you have we are interested in cities that each spends $100,000 on TV and $20,000 on radio. So you are interested in this object f of 100,000, 20,000, and the confidence interval is 10,985 to 11,528. But if you look at the prediction interval, which is where the y lies, not where this f of 100,000, 20,000 lies, but where y lies, and y is like this f of this quantity plus epsilon, then you see that the prediction interval is this 7,930 to 14,580. So if you consider these two intervals, this interval, the prediction interval, is wider than the confidence interval, because like if you look at the upper limits, this is 11,000, so this is 14,000, so the upper limit is higher, and if you look at the lower limit, then in the confidence interval, the lower limit is 10,985, in the prediction interval it's 7,930. So the lower limit is lower, the upper limit is higher, and hence like this prediction interval are generally wider than confidence interval, and that's because of the excess noise. Okay, so we'll take a short break and see look at this model with like this model's in R. Okay. So we've already seen the basic formula for simple and multiple linear regressions, and we have seen how they can be used to analyze data sets where you have predictors more than one in the case of multiple linear regression. And then we also considered some criterion for model fit, so the R squared, the residual sum of square, and other things. So in this part, we'll talk about how to just evaluate those quantities using just R. So R will just give you the formula for the model fit, or R will give you the p-value. And so if you just run a linear regression in R, so there is a command in R, so then you do the entire thing, and then you can access the different part of the regression. So you can access some of the coefficient, you can access some of the p-values, you can, okay, so in case you are not familiar with this libraries command, so it actually is used to load libraries and that are not included in the base R distribution. So for example, we'll be using the library ISLR2, so that's like the library for the book that we are using, Introduction to Stat Learning with R. So, so this library will have certain data sets, it will have some functions, so on. So ISLR2 package can be installed like the way you install standard packages. And we consider this data set Boston. So it's the data set of housing prices. If I'm not wrong, then it's like the housing prices in Boston. So there are 12 predictors, and then there are description of this of those predictors in the housing data set. So what you can do is like, so you can do like head of this Boston data set, give you like a quick glimpse of what are the predictors, what are the 4 or 5 values, and so on. So it has these predictors, CRIM, ZN Indus, or whatever. But yeah, you can just run the command $Boston, and that will give you the description of the predictors. So it's CRIM is the per capita crime rate by town. ZN is the proportion of residential land zoned for lots over some 25,000 square feet. So CHAS is like whether it's close to Charles River, something like that. So if you're close to Charles River, then the prices would be higher. And then there are a bunch of other variables, and MEDV is like the median value of owner-occupied homes in $1,000. So MEDV would be our response, and the others variables will be our predictors. So using this head of Boston, so you can actually get a glimpse of the first 5 of the 506 neighborhoods. Okay, now we come to the most important function in this linear regression, which is called the LM function. So this is the name of the variable that we are in which we are storing the entire linear model. So lm.fit is just a name, it's not a command. And then you run lm made of v, so that's the median value, and lstat. So we are regressing MEDV with lstat. So is the lower status of the population or something like that. So this is your response, this is your predictor, so this is a simple linear regression, and the data is Boston. And you can also just attach the data, so it means that R has access to the data Boston, and then you just run lmfit without this comma data Boston, because you have already attached the data. So this gives you the entire linear model, and then you can see that if you just type lm.fit, then it gives you all the things about this linear model. So you call, so this is the formula, so and then you give the coefficients, which are the intercept, and the coefficients of the intercept is beta naught, and the coefficient of this one is beta 1. So it's beta naught hat and beta 1 hat. So these are 34.55 and minus 0.95. And also you can run a summary. So it says that, okay, the residuals, if you look at the residuals, so you do a fit, and then you get the yi hats, then you compare the you compute the yi minus yi hat for all the 506 neighborhoods, and then this is a vector, so you can compute the minimum value and the maximum value and like the median value and so on, and you can compute, and this gives you like the coefficients. So we have already seen that the coefficient beta naught hat is 34.55 and the beta 1 hat is minus 0.95, but you also get their standard error. So we have already discussed how to get the coefficient of standard error in the last class. So it's like the AC of beta naught hat, and this is the AC of beta 1 hat. You also have the corresponding t values, and we have also discussed how in the large n limit this can be approximated by the normal distribution, and corresponding to those you have the corresponding p values, and these p values are very small, which means that the intercept is significant, and the coefficient for this lstat is also very significant. So LM in this case is an example of list. In R, list gives you a bunch of things associated with the linear model. So you can just write names of this LM. So names of a data set gives you the variables in the data set. But if you write names of lmfit, you just get what are the things that are included in lmfit. So you have the coefficient, you have the residuals, you have the rank, fitted value, etc. So only the coefficient and residuals are shown in the summary. To access the coefficient, so there are many ways to access the coefficients. You can just write lm.fit $coefficients, and that gives you intercept and lstat. Similarly, if you want to access residuals, you just write lm.fit $residuals and so on, but there's a bunch of other other commands that also give you the same thing. So you can use the conf_int function to create confidence interval for the coefficients. So the confidence interval is like their estimate plus minus some constant times the standard error, which I've discussed that for large n you can approximate this constant by 2, and so it says that with 95% probabilities your intercept lies between these two numbers 33.44 to 35.65, and LSTAT lies between minus 1.02 to minus 0.87. So you see that your intercept, like the beta naught hat, is 34.55, that lies between these two numbers, and your LSTAT coefficient is minus 0.95, that lies between these two numbers. So you have the mean and then you have the two cutoffs. So it says that, okay, you take two numbers within which like the estimate lies, and you say that, okay, so within this confidence interval there is a 95% chance of your actual coefficient lying. So there is also a function called predict. So you use predict lm.fit and data frame LSTAT C 5, 10, 15. So it means, so you consider the variables which are 5, 10, and 15, and then it gives you, for these three numbers, it gives you the fitted value and the lower and upper bound, so the confidence interval. So these are the prediction confidence interval. Okay, so this is the confidence interval and this is the prediction confidence interval that we discussed a while ago. So the confidence interval is the region in which your fx lies with probability 95%, and prediction interval is the interval in which your y lies with 95% probability, and we also discussed that prediction interval are larger than the confidence interval. So you see that in this case the prediction interval is 29.05, 29 to 30, and is 17 to 42. So again, the lower one in the prediction case is lower than this one, and the upper one is higher than this one. So the prediction confidence interval are wider than the original confidence intervals. As we have noted that prediction confidence interval are wider, we have specified the new data to be 3 points, 5, 10, and 15. And we do so in a like a data frame setup. So if you do not include the data frame, it will only show the predictions and the intervals from the training set. So far we have discussed how to get hold of an object called linear model, or LM, in the R. So you can extract all forms of data from this LM. Next, what you do is like we do something visual. So we consider like a visual aspect of this linear model. So we just plot this LSTAT versus MADV. So LSTAT was our predictor and MADV was our response. So we just plot it. So as the lower status of the population increases, the housing price goes down. And you can use like the command AB line to fit a line through your through your data. So AB line is a command for fitting lines, and if you write AB line of lm.fit, so for AB line, with AB line you are trying to fit a straight line. So for a straight line you only need intercept and the slope. So when you write AB line of LM fit, so it gives the intercept as the intercept of the linear model and slope as the fitted coefficient of the linear model. So AB line of LM fit actually extracts beta naught and beta 1 hat, and then beta naught hat is your intercept and beta 1 hat is your slope, and that enables you to draw a straight line through the curve, and you can adjust the line width, you can adjust the color, etc. You can play around with other things, and then you get like how this least square line will look like if you plot it. So you can also use PCH command. So if you want to use different symbols in the same plot, so here we are plotting 1 to 20, so these are like the numbers 1 to 20 and 1 to 20, and then because it's like x equal to y, so x is 1, 1, 2, 2, so this is y equal to x line, and we're using different symbols. So these are the symbols. So PCH equal to 1 means this circle, PCH equal to 2 means this triangle, and so on. So if you just include PCH in this plot with like PCH2, you will get the entire thing with the triangles. So plot on the linear model actually generates multiple plot, and so if you just write plot of LM fit, so here, okay, so you're just plotting L stat versus med V, and then you're just adding the line using this LM fit. But if you just plot LM dot fit, so okay, this command par mf row, this is like a command to like split your windows into like 2 by 2 matrix. So you have your entire screen, you split it into 2 by 2 matrix, and then you run this plot, and then what you get is like these 4 plots. So these plots are show various things about a linear model. So for example, you can compare plot the fitted values and the residuals, and if they do not form, okay, they have tried to fit a line, but if they do not form a pattern, then your residuals are well distributed, and then the model is a good fit. So you can also plot the theoretical quantiles versus the standardized residuals, and if your model is a linear model with normal errors, then the standard residual will have a close to a normal distribution, so the QQ plot will match. But obviously we are computing this from not like a simulated data, we are computing this from actual data, so there will be some deviations. So you can also plot fitted values versus standardized residual. Instead of the residual, you do a standard residual, and you can also compute the leverage. So leverage is something that it means that whether one point significantly affects your fit or not. So we'll come back to leverage later. So you can also plot the residual directly using this plot lm.fit and then this rstudent. So rstudent lm.fit gives you standardized residual, so you get something like this. So this is the same as this plot. You can also compute this leverage using something called had values. So we'll come back again, what I mentioned, that we'll come back to this leverage notion later in the lecture. And so what it means essentially is like you have 506 data points, so n is equal to 506. So it says that which one of them are like has high leverage. So what is meant by leverage? It means like if you change that observation a little bit, so the entire least square line will change. So if it has a high leverage, so it will change the least square line if you change it too much. While if it's a low leverage, then it means that if you change it a bit, the least square line will not change that much. So if you look at this data point, so suppose I'm looking at this point, so if you just perturb its size slightly, the least square line will not change that much. But if you are like considering these points are like outliers, and if you suddenly move some of them, like then the least square line will change. Okay, so we'll get back to these concepts later on. And finally, we consider multiple linear regression. So this was the simple linear regression. We only consider regression with the median value of house with the lower status of the population. And now you can look at we want to look at like multiple predictors simultaneously. So what we do is we run the LM command, but instead of just one variable, we just add plus x1 plus x2. So plus x1 plus x2 is just a way of telling R that we want to consider the variable x1 because it's the variable x2 and x3. So again, this is the predictor, these three are responses, and then LM dot in the housing data set, so in the Boston data set, what we do is like we try to fit a linear model of the median value with when the predictors are LSTAT and the age. I think age is the so age variable is the proportion of owner occupied units built prior to 1940. So yeah. So you're regressing on these two variables, and this is an example of multiple linear regression. So after you fit, you get the residuals, so you can compute the mean, median, and the first and third minimum, and the median and the first and third quantile, and the maximum of these residuals, and you can also compute the coefficients. So here it will be in this case, this will be 3 coefficients. So one is the intercept, and the other 2 would be the coefficient for the LSTAT and edge. So these are the coefficient for LSTAT and edge. And you also get the standard error for the same. You get the t-value and you get the p-values. So the p-values for all of them are significant. So we've already seen that the 2 p-values for the intercept and the LSTAT are significant. So in this case, you see that if you do not want to set your cutoff too low, then the age p-value is also significant. So age has a significant effect on the value of your housing. So there is also a shorthand for including all the variables. So here we have included only LSTAT and age. So suppose you consider regression with all the variables, all the 12 variables. So you just write mid, v, and tilde. So that means you're considering all the variables. So when you do that, so you get the range of your standardized range of your residuals, and you get all the coefficients. So you have 12 coefficients for the crime, the zone, the whether it's close to church, whether is the one for the lower status of the population, and so on. So you have 12 variables and one intercept, so you have 13 coefficients. For each of them, you have your estimates, beta naught hat, beta 1 hat, up to beta 12 hat. You have their standard errors, you have your t-values, and of course you have the corresponding p-values. So for example, we see that this coefficient is not significant. So also we can look at the F statistic. It says that, okay, the p-value is 2.2 times e power minus 16. That means that the p-value is quite small. it means that at least some of the predictors are useful in predicting the response, or there is a relationship between at least one of the predictors and the response. You can run the summary, names of the summary, so you can get what are the things that are listed under the summary, and then you can call one of them individually, like say you're running summary lm fit, and then you just want to evaluate the R squared, you get 0.734307, or you want to get, yeah. So these are job object and the summary, so you can call them individually. I think, yeah. That's all for today. So we have considered linear regression, multiple linear regression, and how to fit those models in R. So this will be uploaded, our codes will be uploaded in the Canvas, and then in the next lectures we'll see how to include like qualitative variables and stuff like that in your predictors.